Hello, and welcome to Lecture 30 in this Introduction to Proof series. Today we're going to be covering Section 6.2 in a general introduction to the art of mathematics, which is about the properties that relations may have or not. So let's get going. First, the sort of layout for today. In this first section called Intro, we'll actually introduce the properties that we're talking about. There are 5 of them. In the next, too quick. In the next section, we'll be talking about actually equivalence relations and ordering relations. Those are our goals to sort of emulate. And finally, we'll have a section where we talk about visualization tricks to think about the properties we're going to deal with. So yeah, 2 relations stand out as models of important behavior. Just say what they are: equals and less than or equals. There's some people who might say we should prefer less than, but I'm taking the tack that less than or equals is primary. What are these things? Why are these things so special? I don't think I have to convince math people that equals is really important. Less than or equals is our prototype for putting things in a row, putting things in order, and that's a pretty handy kind of thing, of tool to have around. So we're looking to, when we come across new relations, to sort of put them hopefully in one of these categories, that they behave more or less the way equals does, or possibly that they behave more or less the way that less than or equals does. The former are called equivalence relations, and the latter are called ordering relations. So yeah, if we can figure out that some new relation we're handed, or maybe we discover it on our own, but it's one of these 2 types, it turns out there's a lot of powerful machinery that can be brought to bear to prove things about your new relation. So what is it about equals that makes it so special? I mean, that equals is a useful tool, obviously, but it took a while for people to realize what are the exact properties of the equal sign that make it so powerful. There's 3 properties, and equivalence relations are those that have those 3 properties. Ordering relations are also defined by 3 properties, and this is the 3 properties that the less than or equal sign satisfies. So here's the plan. We're going to lay out a whole pile of properties. Actually, not that many. There's 5 properties that a relation may or may not have. And then we'll think a little bit about how to prove it when they do. Then we'll proceed to define equivalence relations and ordering relations. All right, so what are these properties? Well, the first one is called reflexivity. I'm wondering whether I'm being too pedantic using these strange forms of it. I think people more often say the reflexive property. It depends on what part of speech you're trying to use. Reflexivity, irreflexivity, symmetry, antisymmetry, and transitivity. So again, you might say the symmetric property, or the antisymmetric property. You could say the transitive property, or you can be a little more fancy and say transitivity is the property that the relation enjoys. Okay, so let's take a look at this table in the General Introduction to the Art of Math. It's on page 250. It has these properties all listed, and there's basically 2 elements in here. A, the name of the property, so 3 elements, then a formal definition of it, and then a kind of informal way to think about the property. The setup on all of these is the same. You're talking about a relation R on a set S. And as we talked about in the last section, when you say a relation is on a set, it means that it is a subset of S cross S, or that it's made of ordered pairs where both the left and the right element in the ordered pair come from the same set. So a relation R on a set S is reflexive, if and only if, for all A in the set S, A are A. That's I think the informal way of saying it is pretty nice. Everything is related to itself. That's not always the case. I mean, you're used to that with the equal sign. Less than or equals actually also has that rule because it includes the idea of equals. But for instance, strict less than, you can't say that 7 is less than 7, right? It doesn't have that reflexive property. A relation R on a set S is irreflexive if and only if. Here, what we're saying is for every element of the set, it's not related to itself. Nothing is related to itself. A, not RA. Notice that on both of those first two properties, we got away with using a single universally quantified variable. In the next one, we need two variables. So in fact, that's true for the symmetric property and the antisymmetric property. All right, so a relation R on a set S is symmetric if and only if for all pairs of things, A and B in S. When A is related to B, that implies that B is related to A. That's just the way the equal sign works. If A is equal to B, then of course B is equal to A. We can flip the order around. The way this is said informally is no one-way streets. And we'll see what that means when we get to looking at the directed graph visualization tool for a relation. A relation R on a set S is antisymmetric. This one, this fourth one. Antisymmetric is defined in a strange way. The trick with this definition is that when you satisfy it, you kind of don't. You always satisfy it in a vacuous way. So kind of think about what happens here. You have two things, and I guess we want to suppose they're distinct things, A and B. And they're related in these two orders. A is related to B, and B is related to A. Well, in that case, this property says, hey, what, bud? Those weren't distinct after all. They're equal to each other. You've got a sort of a miniature contradiction. You suppose two things are not equal. Use this property to show that they are equal. So when you have the antisymmetry property, it just is the case that you will never find two distinct things that are actually related in both orders. Because if it happened, they would actually be equal to each other and thus not distinct. So what that creates is you only see one-way streets. If something is connected in both directions, then, well, it sort of collapses into a single point. Finally, transitivity. The transitive property, I suppose I should read it the way it says. A relation R on a set S is transitive if and only if for all A, B, C in S, when A is related to B and B is related to C, that implies that A is related to C. Now, if you think of these R's as roads, there's a road from A to B, and there's a road from B to C. But this implies that there's a direct route from A straight to C. That is, there is a road from A to C. Yeah, like it says, whenever there's a roundabout route, there's a direct route. So, well, I guess that's the chart on page 250. Let's get back to the slides and see what else we're supposed to do. Oh, that was it for that section. Cool. So our next section will actually see the definitions of these things that act like equals and these other things that act like less than or equals. And that should be fun. So, well, actually, it's not fun because it's just three things and you just got to remember them. It's a memorization moment. When you have an equivalence relation, it must have these three properties. Or put it a different way. If you hope to show that something is an equivalence relation, you have to verify these three properties: the reflexive property, the symmetric property, and the transitive property. So if I say it in terms of equals, things have to be equal to themselves. When they're equal in one order, they're equal in the other order. And the transitive rule: when A is equal to B and B is equal to C, then A is equal to C. So that's what equivalence relations need, those three properties. Ordering relations have these other three properties. Actually, I shouldn't say other because only one of them's changed. It's only the middle one. What was symmetric? The symmetric property is now the antisymmetric property. So there's a lot in common between them. I want to note that in both cases, the complexity of these properties goes up as we go down the list. Reflexive has got a single universally quantified variable in it. Symmetric or antisymmetric both have two such quantified variables, and the transitive rule requires three. All right, let's get into how we kind of think about these different properties of relations with our visual minds. The first way to do this, I think, is smart, is to think about graphs in the plane. So this only works when you're talking about a relation on the real numbers. So if you have a graph that's if you have a relation on the real numbers, and you look at the graph of that relation, in other words, the pairs of points, the pairs of ordered, the ordered pairs of values from R. Anyway, if it's reflexive, the line y equals x is part of it. That is, you may see some strange looking graph, but hidden within that graph is going to be that straight line at 45 degrees that goes through the origin, the y equals x line. Graphs of symmetric relations on R are, symmetric. So what sort of symmetry are we talking about? Well, can I kind of visualize it for you? This way. If I've got the x and y axes like that, there's a line on 45 degrees, y equals x. Symmetry means across that line. Mirror images in the line y equals x. Maybe I'll do an example of that when we go into Desmos. Is it clear what would happen with antisymmetry? Well, then the mirror image across the line y equals x is not there. If it's on one side, it will not be on the other side. So, and vice versa. Yeah. Transitivity is hard, and so I'm going to pull up a Desmos graph to show you how transitivity works. Now, I'm thinking about the divisibility relationship here. So I have a couple of pairs already on the screen, 2, 4, and 4, 12. And they are on there because they're elements of the divides relation. 2 divides 4, and 4 divides 12. But we know that, well, maybe we don't, but it turns out that the divides relation is transitive. So what does that mean in this case? Well, if 2 is related to 4 and 4 is related to 12, it should be the case that 2 is related to 12. Now, what that looks like is a little complicated, but I'm going to show it to you a step at a time. Above 2, we have this point, 2, 4. Right? So we move over to the y-axis and find that point, the height 4 on the y-axis. Then we zip across to the x-axis and pick up 4 down there. So basically this construction so far was just to create something on the x-axis that has the same value as the y-coordinate, or the second coordinate of that point. Then we move up to our point, because 4 is related to 12, right? And finally, we zip across back to 2, and there should be a point right there. That is, if you're transitive, you do this little weird J-shaped thing, you're going to see a point there. Now, there would also be, for instance, a point here, because 4, 8 is also in the divides relation. And so there'd be a point here. There's sort of a reflection of all the points that are above 4 in the things that are above 2. All right, so, and I guess I promised I was going to talk about symmetry. Let's just kill all this junk off. Except for that one. What does symmetry look like? Well, plot the line y equals x in here. And you're symmetric if whenever that guy's in here, so is this guy. The purple one is symmetrically across the line y equals x from the blue one. Anti-symmetry would mean that purple one You may not have a point in that location. It would be disallowed if you were to have an antisymmetric relation. But you can have, well, you could change all kinds of things. Like maybe have 2, 3 be that point. Well, then that needs to be 3, 2. You see, we've picked up the symmetrical or mirror image looking thing again here. All right, back to the slides. The other way to visualize relations is with digraphs or directed graphs. I wonder if it would be smart for me to make a few drawings in this. A digraph is just a picture with nodes and arrows between the nodes. So I'm going to make one with 4 nodes, or some people call these vertices. Either term is fine, they're synonyms. And then some arrows that run between these things. I'm not sure. I'm just making one up right now. Okay, this has no strong meaning. But if we have a directed graph showing relation, then when it's reflexive, you will see loops. Like, if this thing is supposed to be related to itself, there's going to be a loop that goes from it to itself. And the digraph for a relation that is that it satisfies the reflexive property, that's universally quantified. Over every element, there's supposed to be a connection from it to itself. So you'll get loops everywhere. I have just created a reflexive, I've created the digraph for a reflexive relation. I have no idea what that relation is. I didn't even label the nodes. But if you look at the thing and you see loops everywhere, you've got something that's reflexive. Symmetry is another property we had, and what you will see in symmetry, in the digraph for a symmetric relation is there'll always be two-way connections. This thing has not got that right now, but I could make it so. I could say, well, if that one goes that way, I'll make another row that goes the reverse direction from it. Another one here that goes in the reverse direction of that one, and another one that way. As long as you've got any connections that exist, there's also the connection in the other direction. You've got symmetry. That's the way to visualize a symmetric relation. Antisymmetry. That means what I had originally was antisymmetric, right? If you don't see these double two-way connections, it's antisymmetric. Here's a nice example of antisymmetric. You know the game Scissor, Paper, Rock? I have this example in the book somewhere. It's just not true that paper covers rock, and rock smashes scissors, and scissors cuts paper. These connections all go in one direction because we want one outcome to beat the other. So yeah, they don't go two ways. You only have the one-way connections. What do you do when both players have scissor? Should we put a loop there? I think in this game, no. It's just a tie, and you start over if you both have scissors. All right, so one-way connections. That's the hallmark of a antisymmetric. Really need to be careful the way I say this. The hallmark of the digraph for an antisymmetric relation is the connections are all one way. Okay, so for the transitive rule, this is what you see as shortcuts. The base case is something like this. You may have 3 things, A, B, and C. And if there's a way to get from A to C via some waypoint like B, then there needs to be one that goes the straight route. That is, when there's a long way around, there's got to be a short way, a direct way. So you will always see shortcuts. If you have a relation that has a big string of things that are connected like that, A is to B, and B is to C, and C is to D, that one, were it to be transitive, you would need to have a shortcut and a shortcut. And because of this one and that one a shortcut. There's a direct route from the beginning to the end. So lots of shortcutting of things when you have transitivity. All right. Oh, what's not in the digraph? What we're going to look at next is sort of how to spot what won't happen if you've got one of these properties, and thus be able to say right away, hey, that one's not reflexive, or that one's not transitive. So first it says, let's do the exercise on page 253. So let's see what that is. I'll have to look. We're almost there. You just scroll. What is this? Oh, find logical negations for the formal properties defining each of the 5. It's a weird double use of the word properties there. But anyway, like when we were talking about the reflexive property, I want to figure out what it means to not be reflexive. Might as well point out that's not the same as irreflexive. Let's pull this out because we're going to need to see a little better. Well, it's the negation of for all x, xrx. I think I was using a's before, but I hope the change of letter isn't going to bother you. How do we negate a universal sentence like that? You turn the quantifier into the other type, and you negate the thing. And negating a relation is pretty simple. You just put a slash through it. So, okay, that's one. What about, wait a minute, what does that say? There is an x, so that x is not related to x. Or if what we're looking at the diagram, there's a point that doesn't have a loop at it. Oh, we'll come back to these. What is the next property? Symmetry. So let's figure out what not symmetric looks like. That's the negation of for all. Let's return to the proper letters A and B in our set. What did it say? If A is related to B, then B is related to A. Oops, coming off the edge here. Sorry, that's a little bit tight. Doesn't quite all fit on the page. But I think I'll make it fit when I actually do the negating part. We'd negate this by changing the quantifiers to exists. And we need to negate that conditional. That would be A is related to B, and B is not related to A. The if part is true, but the then part not. And that gives you the negation of a condition. So this would be what we would need to see if we said we were not symmetric. Or this was the sort of thing, if you saw it, you'd know, oh, that relation's not symmetric. I'm going to skip antisymmetry for now, and because I can. The property for antisymmetry is a little tough to work with. Okay, maybe I shouldn't cheat. Let's do it. Not antisymmetric. What is that going to look like? Well, we're negating something that's universally quantified with. How come my A ended up being right side up? Not the negation of a universal thing with 2 inputs, 2 variables universally quantified, and the antecedent of it, or the statement after the quantifiers was this: if A is related to B, I'm really having trouble making A's A related to B and B related to A implies A and B are equal. Well, that's actually not so hard to negate because, again, the universal becomes an existential. Does there exist an A or there exists a B? You can still work those together. This would be true, and that would not be true. A is related to B, and B is related to A, and A is not equal to B. I probably would like to say that with the last thing first. There exists A and B that are different from one another, such that A is related to B and B is related to A. That's what the negation of antisymmetry looks like. And finally, we got to say what's the negation of transitive. What does not transitive look like? Well, the property for transitive was universally quantified with 3 variables. And what do we have? That A is related to B and B is related to C, implied A is related to C. If we carry out that negation, it becomes existentially quantified. And we just need to negate this if then. Well, that's nice because it turns into a string of ands. The first the if part of our implication will be true, A or B and B or C, and the not of that, A is not related to C. All right, so let's go back to the slides and see how this all plays out in the diagrams. I can tell you this slide is just going to say, hey, let's go through the things in Giam where they appear. The diagrams are there. So pull Giam back up to the fore, and it starts on the very next page. So what do you not see when you have a reflexive relation? Well, again, I should say the diagram. What do you not see in the digraph of a reflexive relation? The red arrow is pointing at you what you should not see. If it's reflexive, everybody should have a loop. And this is a relation where one of the things is loopless. So not cool. What do you not see when you've got an irreflexive relation? Well, then nobody should have a loop. So this guy here, sitting here, B, that has a loop in it, that's the one that tells you, hey, this thing is not irreflexive. Okay, you're symmetric if whenever you see a pair of nodes that are connected, you also they're connected in both directions. So this is what you don't see. You don't see something where there's a one-way connection between A and B. See how C and D have the two-way connection? They're all good for the symmetry property. But this single or unidirectional route from A to B, that tells you this is not a symmetric relation. Antisymmetric means everybody ought to only have one-way streets between pairs that aren't. If they're connected, they should be connected with a one-way street. And here we're seeing a two-way connection, so not antisymmetric. And as has been the case all along here, the transitive property is the tougher one to understand. But here it is. You should never have a missing direct route or shortcut when there is a long cut. That is, when there's a route that goes from A to C via B, there needs to also be the route that goes straight from A to C. So this, that red thing's not really there. What's the red dashed line is missing, and that's why this is not transitive, because we've got a roundabout way to go from A to C. If it were transitive, there should be this direct route. Okay. Well, that brings us to the end of this section. There's a lot of material in there. I think we've gone through it pretty thoroughly. So I guess we'll call it a day there, and have a good rest of your day, and hopefully I'll see you for lecture 31. next time.